amber, vermilion, teal, and chartreuse, violet, magenta, let's all raise our
Oh,
voices.
hey Max.
Howdy Optima. Nice dance, but what's up with the colors song?
Coloring is my passion and the reason I started studying optimization.
I'm intrigued. Tell me
Color
more.
wheel's grown bigger, it's expanding, just like your mind is demanding.
It all started when I was 5. I was coloring a map in my coloring book.
This looks familiar. I think I had the same coloring book.
I would be surprised if this map didn't look familiar. Anyway, when I started coloring the map, my dad saw it and asked me to try to color it in a way that no two bordering states have the same color.
That's easy even for a 3-year-old.
Right, but he wanted me to use no more than 4 colors.
Oof. That's tough. Have you done it?
Yes, I have.
Was your dad impressed?
Yes, and he told me that any map can be colored with just 4 colors.
How did he know?
As I learned later, this follows from the 4-color theorem.
Amazing. There are theorems about coloring geographical maps. What a waste of time. I am glad I am not majoring in math.
Don't jump to your conclusions so quickly. The theorem is a lot more general than this, and the map coloring is just a cute example illustrating it for the general public.
So, what are the real useful applications then? Does the humanity really needs mathematicians' help with coloring?
Graph coloring has tons of useful applications, including sports scheduling, timetabling, bandwidth allocation and telecommunications, and many others. You can even use it to solve Sudoku puzzles.
Sounds fascinating, but why did you say graph coloring?
Because this is what the 4-color theorem is about. The theorem is stated for coloring in graphs.
What type of graphs?
A graph is an object consisting of 2 sets called vertices and edges. The vertices are also called nodes, dots, or points, and the alternative names of edges are arcs, links, or lines.
So, the edges are used to connect pairs of vertices.
Exactly. And we call such pairs of vertices adjacent or neighbors.
Looks like the same thing as a network to me.
Yes, these 2 terms are synonymous, with a graph essentially being a mathematical abstraction of a network. So, a network is a more broad term that can be used in various contexts.
Such as social networks, telecommunication networks, transportation networks, right?
Precisely.
I love networks, especially after we used a network when we solved the Lonely Night puzzle.
Yes, graphs and networks are very useful for modeling many real-life situations.
Who was the first to come up with such a wonderful idea? Perhaps ancient Greeks.
You would think so, but in reality the origins of graph theory are attributed to Euler, who used a graph to solve the Königsberg Bridge problem in 1736.
What's the Königsberg Bridge problem?
The city of Königsberg in 18th century Prussia was split into 4 parts by Pregel River. These 4 parts were connected by 7 bridges shown in red in the figure.
I see that the graph representation is built by using nodes for the land parts and edges for the bridges, right?
This is correct.
I guess Euler was looking for an optimal tour between the parts.
Kinda. He was looking for a tour that would start in one of the parts, visit all 7 bridges exactly once, and return to the original location.
Why do you say kinda then? Sounds like a tour to me, like the one we built to solve the Lonely Night puzzle, isn't it?
Not exactly. In the Lonely Night puzzle and in the traveling salesman problem we are looking for a tour that visits every node once. This is called a Hamiltonian tour. And here we are looking for a tour that visits every edge once, and each node can be visited multiple times.
Okay, you are right, I'm less right. Does such a tour have a name?
Yes, it is called an Eulerian tour.
Makes sense. I would imagine that the number of edges is larger than the number of nodes in most cases. Is finding a Eulerian tour even harder than finding a Hamiltonian tour then?
It is actually the opposite. A Eulerian tour is easy to find whenever one exists. In fact, we can prove that a Eulerian tour exists if and only if the degree of every node in the graph is even.
I can see why. You need to be able to leave a node every time you enter it.
Right, with the exception of the node you start at. But in that case you need to return to it, so the degree of the starting node must also be even.
For example, since there are nodes of odd degree in the Königsberg graph, it has no Eulerian tour. But if we adjust two edges shown in green, all degrees become even and we can easily find a Eulerian tour.
That's a great example, Max.
Cool. Now, can you finally tell me about graph coloring?
Sure. To obtain a proper vertex coloring, we need to assign colors to all the vertices so that no two adjacent vertices have the same color.
Now I see the map coloring connection. You represent each state by a node and build an edge between two nodes if the corresponding states have a common border.
Right. And in the minimum vertex coloring problem we need to find a minimum number of different colors required to color the graph properly. This minimum number is called the chromatic number of the graph.
Okay, this is a reasonable definition, but I don't see how the four-color theorem can be correct. I can easily draw graphs that require more than 4 colors for a proper coloring. Look at this graph for example. Since all possible edges are present, I have to use a different color for every vertex, so I need 5 colors.
Yes, you do. Your graph is complete because it has no missing edges. The set of vertices of such a graph is called a clique.
Like in a high school clique.
Exactly.
I hated those.
Me too, but I love looking for maximum cliques in graphs, it's fun. And it helps with coloring, because whenever you find a clique with k vertices in your graph, this means that you need at least k colors for a proper coloring.
That's exactly what I'm saying, you need a new color for each vertex in a clique. So, how can you claim that 4 colors will always be enough?
Well, not always, but 4 colors are always enough for coloring any graph that is planar.
What is planar?
A graph is planar if and only if it can be drawn on the plane so that its edges don't intersect. Clearly, a complete graph on 5 vertices is not planar, because there is no way you can draw its edges so that they don't intersect.
Indeed. So, the 4-color theorem doesn't apply to this graph.
Correct. But it does apply to a clique on 4 vertices.
I can see that, it is easy to draw without any edge intersections. I wonder if the 4-color theorem is easy to prove.
It does look simple, but the only proofs we have to date rely on computer software. There is still no simple mathematical proof, despite many attempts over the past couple of centuries. Maybe you can do it?
LOL. Very funny. I guess I could develop an IP formulation for graph coloring though, so we can solve it in practice.
Sure, go for it.
Okay, suppose our graph has n vertices. I define 2 types of binary variables. Xik indicates whether the vertex I is colored using color k and yk indicates whether color k will be used at all.
So far so good, but do you really need to try n colors? This may not be a good upper bound on the number of colors, because you will only need n colors if the graph is complete.
Right, but how do I find a good upper bound?
You can typically get a much better upper bound by applying some simple heuristic to find a feasible coloring.
What's a heuristic?
It's essentially a common sense strategy for getting a feasible solution to your problem.
I know how to develop one for the graph coloring. You start by using the first color for the first vertex, and then assign each next vertex the lowest numbered color that was not yet used for any of its neighbors.
Makes sense. This is what they call a sequential coloring heuristic.
This is exciting, it even has a name. Let me try it on the graph we drew before.
Sure thing.
So, the graph has 7 vertices, but I know that I will not need more than 4 colors.
How did you figure that out?
Easy peasy. If at some step of our heuristic k colors have been used so far to color the previous vertices, when do we need to use the k plus first color?
Only when all the k colors were used for the neighbors of the vertex I we are about to color.
That's right. And the maximum number of colors that the neighbors of a vertex can use is the degree of that vertex, isn't it?
Yes.
So, we will never need more than delta plus 1 colors, where delta is the maximum degree of a vertex.
Great observation, Max. Since the maximum degree in this graph is delta equal to 3, we will need at most 4 colors as you said.
So, I guess I could use delta plus 1 as the upper bound on the chromatic number in my IP model.
You could, but the heuristic can potentially give you an even better bound.
We don't know unless we try. Let's see what we get in our example. Okay, I color the first vertex with the first color, which is red. Then, since the second vertex is a neighbor of the first one, I use green.
Then red can be used again for the third and fourth vertices.
Excellent. Then we use green for the next two vertices.
And now we cannot avoid using blue.
Too bad, but we were still able to improve the bound given by delta plus 1.
And the bound of 3 is way better than n equal to 7 you use in your model.
That's right, I definitely need to correct that. So, using C instead of n for the upper bound on the number of colors helps us reduce the number of variables by a lot. We minimize the objective, which is the total number of colors used.
And the first set of constraints ensures that each vertex is assigned exactly one color.
The second set of constraints guarantees that no two adjacent vertices use the same color.
And the last set of constraints says that you cannot color a vertex I in color K if that color is not used.
Isn't this beautiful?
It is just amazing.
I concur with this assessment. Now, how do we use graph coloring to solve Sudoku?
It's actually pretty simple. You just need to construct a suitable graph, where a proper coloring will correspond to a Sudoku solution.
Let me think. I think I got it. We create a vertex for each Sudoku cell, so there will be 81 vertex. Then we draw an edge between each pair of cells that cannot be assigned the same number in Sudoku.
I assume that the colored vertices correspond to the cells with given numbers in the puzzle.
Right. And I only illustrated the edges for a corner vertex and for a vertex in the middle. I was too lazy to draw all the edges.
Naturally, the vertices in the same block or row, or column form a clique on 9 vertices.
So, we need at least 9 colors for a proper coloring, and an optimal coloring will achieve this lower bound.
You are a genius, Max.
I am not sure about that, but I can certainly pick better music.
The song you played last week is still stuck in my head.
That's what I'm talking about. Show must go on.